What if the universe you live in isn't playing by the rules we thought governed everything? Imagine for a moment that the laws of physics, the very foundation of our reality, suddenly faltered or twisted in ways we can't explain. Picture spacecraft veering off course for no reason, stars dipping into shadowy enigmas, or entire regions of space exerting impossible forces. These aren't just wild ideas, they're real phenomena that have left scientists baffled and searching for answers. Welcome to a journey through the cosmos unlike any other, where we uncover 25 moments when space itself seemed to defy logic and rewrite the rules of science. Each case is a doorway into the unknown, challenging everything we thought we understood about the universe. By the time this video ends, you might just start questioning what we truly know about the cosmos and our place within it. Stay with us as we unravel mysteries so compelling they could redefine the very fabric of reality. Now turning to the first case, let us explore the Pioneer Anomaly. Launched in the early 1970s, the Pioneer spacecraft were designed to venture further into deep space than any human-made object before them. For years, they journeyed outward, sending back invaluable data about our solar system. But as they traveled beyond the planets, something strange started to happen. Both Pioneer 10 and Pioneer 11 began to drift off their expected trajectories. Instead of following the carefully calculated paths laid out by scientists, the probes seemed to experience a tiny but persistent force pulling them back toward the Sun. This deviation was so slight that it took years of data analysis to even notice, but once discovered, it sent shockwaves through the scientific community. What could cause this unexpected motion? Was it some previously unknown force of nature, a glitch in the spacecraft's design, or perhaps was it an error in our fundamental understanding of physics? For decades, researchers have tried to solve this riddle, proposing theories ranging from thermal emissions from the spacecraft itself to exotic new physics beyond our current models. Even today, while some scientists believe they've narrowed the cause down to subtle thermal effects, others argue that the mystery isn't fully resolved. The Pioneer spacecraft continue to challenge our understanding of the universe, reminding us just how much we have yet to uncover. Moving forward, let us examine another puzzling phenomenon that shook the foundations of astronomy, the discovery of dark energy and its role in the accelerating expansion of the universe. As the next challenge unfolds, let us delve into the groundbreaking discovery of dark energy and its role in the accelerating expansion of the universe. For centuries, scientists believed that the gravitational pull of matter would ultimately slow down the universe's expansion. This seemed logical, just as a ball tossed into the air eventually succumbs to gravity and falls back down. The universe, filled with countless galaxies and immense gravitational forces, was expected to behave similarly. But in the late 20th century, observations of distant supernova threw this assumption into disarray. Astronomers discovered something shocking. The universe is not just expanding, but it is doing so at an accelerating rate. Imagine tossing that ball into the air and instead of slowing down, it starts speeding up, defying everything you thought you knew about gravity. This revelation was so unexpected that it turned cosmology on its head. The driving force behind this acceleration was named dark energy, a term that captures both its mysterious nature and our profound lack of understanding about what it truly is. Dark energy is thought to make up about 70% of the universe, influencing its fate on a monumental scale. But what exactly is it? Is it a new kind of force, a property of space itself, or something even more exotic that we have yet to comprehend? Despite years of research, dark energy remains one of the most perplexing enigmas in physics, challenging some of the most fundamental principles of our scientific knowledge. Its discovery not only altered our view of the cosmos, but also raised profound questions about the ultimate destiny of the universe. As scientists continue to unravel the mysteries of dark energy, they edge closer to understanding its role in shaping the cosmos. Now, let us turn our attention to another celestial puzzle that left astronomers scratching their heads: the strange and captivating behavior of Tabby's star. Now turning to the enigmatic Tabby star, a celestial body roughly 1,400 light-years from Earth that has baffled astronomers since its erratic behavior was first observed. Unlike typical stars which follow predictable patterns of brightness, Tabby's star, officially known as KSE 8462852, exhibits irregular and dramatic dips in its light. At times, the star's brightness has dropped by as much as 20%, a phenomenon that defies standard models of how stars should behave. To put this into perspective, 20% is far too significant a change to be caused by a planet passing in front of the star, as such an event usually causes dimming by only a fraction of that amount. Naturally, these bizarre light fluctuations sparked a wave of theories in the scientific community and beyond. Some proposed that the dimming could be caused by a massive swarm of comets orbiting the star, each one briefly blocking its light as it passed. Others suggested a cloud of interstellar dust or fragments from a shattered planet, but perhaps the most intriguing and controversial idea was that the dimming might be the result of a massive alien megastructure. Picture an advanced civilization building a colossal structure, such as a Dyson sphere, to harvest energy directly from the star. While this idea captured public imagination, scientists remain skeptical as there is currently no direct evidence to support it. What makes Tabby's star so perplexing is that even with years of study and data collection, no single explanation fully accounts for its unusual behavior. Each new observation adds another layer of mystery, leaving scientists with more questions than answers. Could it be a phenomenon we have yet to discover, one that challenges our understanding of astrophysics? Or is the answer hidden among the theories already proposed, just beyond the limits of our current knowledge? As we ponder these possibilities, we are reminded that the universe often surprises us in the most unexpected ways. Moving forward, let us explore yet another cosmic enigma that draws us deeper into the unknown: the Great Attractor and its mysterious pull on our galaxy. Now turning to the Great Attractor, a gravitational phenomenon so immense that it is tugging entire galaxy clusters, including our own Milky Way, toward a mysterious region of space. This colossal force is located about 150 million light-years away in the direction of the constellation Centaurus. What sets the Great Attractor apart as an enigma is not just its staggering gravitational pull, but also the fact that it lies within the so-called zone of avoidance, a region of the sky obscured by the dense plane of our own galaxy, making it exceptionally difficult to observe directly. Scientists first detected the effects of the Great Attractor in the late 20th century, when they noticed that galaxies, including ours, were not merely drifting with the general expansion of the universe. Instead, their movements showed an inexplicable pull toward this hidden region. The gravitational force at play suggests the presence of an incredibly massive structure, one far larger than any single galaxy. Yet, what could account for such unimaginable mass remains a mystery. Some theories propose that this region may be home to a supercluster of galaxies, a concentration of dark matter, or even some form of exotic physics that we have yet to discover. What adds to the intrigue is that, despite decades of research and advanced technology, the exact identity of the Great Attractor remains obscured, as if the universe itself is guarding its secrets. Could it be a massive galactic structure hidden behind the dust and stars of the Milky Way, or does it represent something entirely beyond our current scientific frameworks? Such unanswered questions remind us of how much remains to be uncovered in the vast cosmos. As we marvel at the thought of this hidden force shaping the movement of galaxies, let us turn to another extraordinary mystery that has captured our collective imagination: the first known interstellar visitor to our solar system, the peculiar object known as Oumuamua. Moving forward to one of the most intriguing discoveries of recent years, we arrive at Oumuamua, an object unlike anything we've ever encountered before. Detected in October 2017, this mysterious visitor was the first known interstellar object to pass through our solar system, and from the moment it was spotted, it defied expectations. Its name, Oumuamua, which means scout or messenger in Hawaiian, was fitting for an object that would send shockwaves through the scientific community. Oumuamua's elongated, cigar-like shape was the first clue that it was something extraordinary, measuring roughly 800 meters in length but only a fraction of that in width. It was unlike the rounded asteroids or icy comets we are familiar with. As astronomers tracked its trajectory, they noticed something even more baffling. Oumuamua exhibited unexpected acceleration as it moved away from the Sun, as though it were being propelled by some unseen force. This behavior added to the growing list of mysteries surrounding it, as the acceleration could not be fully explained by gravity or by the outgassing of material like water vapor, which is common with comets. Scientists have since proposed a range of theories to explain Oumuamua's peculiar characteristics. Some suggest it could be a fragment of a larger body that was torn apart by gravitational forces in another star system. Others propose it might be a type of interstellar comet or asteroid made of material we have never encountered before. Perhaps most fascinating of all is the hypothesis that Oumuamua could be an artificial object, potentially an alien probe or spacecraft sent by an intelligent civilization. While this idea is highly speculative, it has captivated both scientists and the public alike, highlighting how little we know about what lies beyond our solar system. Despite extensive analysis, there is no consensus on what Oumuamua truly is, and its brief visit has left us with more questions than answers. As it continues its journey into the vastness of space, Oumuamua remains a tantalizing reminder of the unknown, sparking curiosity and fueling our desire to explore the mysteries of the universe. Now, as we ponder the enigmatic path of this interstellar traveler, let us delve into another cosmic challenge, the perplexing problem of galactic rotation and the hidden forces driving it. Now turning to the perplexing puzzle of galactic rotation, we encounter a mystery that has left astronomers scratching their heads for decades. When scientists began studying the rotational speeds of galaxies, they expected the outer stars to orbit more slowly than the inner ones, much like the planets in our solar system do. However, what they observed defied this expectation. Instead of the outer stars slowing down as predicted by the gravitational pull of visible matter, they were moving at almost the same speed as the inner ones. This bizarre behavior suggested that something was missing, an enormous amount of unseen mass exerting gravitational influence. To explain this discrepancy, scientists introduced the concept of dark matter, a form of matter that does not emit, absorb, or reflect light, making it invisible to our telescopes. Dark matter is thought to make up about 80% of the total matter in the universe, yet its true nature remains one of the greatest scientific enigmas of our time. Despite being undetectable directly, its presence is inferred through its gravitational effects on stars, galaxies, and even the cosmic web. Picture a galaxy as a spinning merry-go-round. The visible stars and gas make up only a fraction of its total mass, while a vast halo of dark matter surrounds it, providing the gravitational glue that holds everything together. But here's the catch: although dark matter is the most widely accepted explanation for this phenomenon, it is still just a hypothesis. No one has ever directly detected a particle of dark matter, and alternative theories challenge its existence, proposing modifications to the laws of gravity instead. The galactic rotation problem is a stark reminder of how much remains unknown about the universe. It pushes us to question the very foundations of physics and to explore new ways of understanding the cosmos. As we leave behind this unresolved enigma of unseen forces shaping galaxies, let us take a closer look at another phenomenon that twists our perception of reality: the way time itself slows near the immense gravitational pull of black holes. Now turning to the mind-bending phenomenon of time slowing around black holes, we delve into an aspect of the universe that seems to rewrite the very fabric of reality. Imagine a place where the flow of time itself changes depending on how close you are to an incredibly dense object. This is no science fiction story. It is a real effect predicted by Einstein's theory of relativity, known as gravitational time dilation. Near a black hole, the immense gravitational force warps not just space but time as well. To put this into perspective, if you were to hover near the event horizon of a black hole, the boundary beyond which nothing, not even light, can escape time, for you would pass significantly slower compared to someone far away from the black hole. For an outside observer, seconds for you near the black hole could stretch into years for them. It is as if the fabric of the universe itself is bending under the intense gravity. Black holes, these cosmic titans of density, are regions where gravity is so extreme that it alters the rules of the universe as we understand them. The warping of space-time near a black hole creates a scenario where time appears to crawl, offering a glimpse into how differently the universe operates under such extreme conditions. Scientists have even speculated that this time dilation could lead to fascinating possibilities, like the preservation of objects or even information for unimaginably long periods. However, it also presents paradoxes that challenge our current understanding of physics. Gravitational time dilation is not merely a theoretical concept. It has been indirectly observed and measured during experiments involving satellites and clocks on Earth, proving that Einstein's predictions hold true even on small scales. But near a black hole, these effects reach a level so extreme that they defy human intuition. This phenomenon forces us to rethink what we know about time, space, and the nature of reality itself. As we emerge from the shadow of these cosmic giants that twist time, prepare to uncover yet another enigma of the universe, the magnetic mysteries surrounding the most powerful magnets known, magnetars. Moving forward, we arrive at one of the most astounding phenomena in the cosmos, magnetars. These are no ordinary celestial objects. Magnetars are a rare type of neutron star, the remnants of massive stars after they explode in supernova. What sets them apart is their jaw-droppingly powerful magnetic fields, which are a quadrillion times stronger than the magnetic field of Earth. To put that into perspective, a magnetar's magnetic force is so extreme that it could disrupt electronic devices from thousands of miles away and even distort the atomic structure of matter if you were anywhere near it. But what baffles scientists is how such extraordinary magnetic fields form and persist. Current theories suggest that these fields are created during the violent birth of a neutron star, as the collapsing core of the star spins rapidly, amplifying its magnetic field to unimaginable levels. Yet, this explanation raises more questions than it answers. Why do only some neutron stars become magnetars? How do these fields remain stable for thousands of years without decaying or collapsing into chaos? And could there be forces or processes at work that we have yet to discover? These questions keep the mystery alive, fueling ongoing research and debate in the astrophysics community. One of the most puzzling features of magnetars is their occasional outbursts of energy, sometimes releasing more energy in a single second than our Sun emits in 100,000 years. These are known as magnetar flares, and they leave scientists scratching their heads. Could these flares be caused by shifts or cracks in the star's solid crust, known as starquakes, or are they linked to deeper processes within the star's magnetic core? Despite their rarity, magnetars provide a unique glimpse into the extreme physics of the universe. They challenge our understanding of matter, energy, and magnetism, forcing us to reconsider the limits of what is possible. With more discoveries and observations, magnetars could unlock answers to questions we have yet to even dream of asking. As we attempt to unravel the secrets locked within these cosmic powerhouses, let us pivot to another conundrum in the universe, the elusive and perplexing missing baryon problem. Now turning to the missing baryon problem, we confront a perplexing mystery that has long puzzled astronomers and physicists alike. Baryonic matter, which consists of the ordinary matter making up stars, planets, and even us, is predicted by cosmological models to account for about 5% of the universe's total content. This seems straightforward, but here's the catch: we can only account for roughly half of it. The rest appears to be missing. Extensive surveys of galaxies, intergalactic gas, and other observable phenomena reveal far less baryonic matter than what theoretical models predict should exist. Where could this missing matter be hiding? Scientists have proposed several theories, one of which suggests that the missing baryons might reside in the hot, diffuse gas of the intergalactic medium, stretched thin across the vastness of space and incredibly difficult to detect. Another tantalizing possibility involves structures known as filaments of dark matter, which might act as scaffolding for pockets of hidden baryonic matter. Recent advances in observational technology have provided glimpses of this elusive material. For instance, astronomers utilizing advanced telescopes and studying the effects of light from distant quasars, which are extremely bright and distant galactic cores, have started to uncover faint traces of baryonic matter scattered along vast cosmic filaments. This finding, though promising, is just the beginning. Solving the missing baryon problem could redefine our understanding of the universe's structure and evolution. It may also shed light on the intricate interplay between visible matter, and dark energy. As we continue to probe deeper into this enigma, we realize the universe remains as enigmatic as it is boundless. With this in mind, we now pivot to another problem that challenges the very fabric of our understanding of the cosmos. The Boötes void, a colossal void in space that defies all expectations. Moving forward, we delve into the enigma of the Boötes void, a staggering cosmic anomaly that stretches our understanding of space to its limits. Imagine a region of the universe so empty, so devoid of galaxies, that it spans an astonishing 330 million light-years across. This isn't your average empty patch of sky. The Boötes void is one of the largest known voids in the cosmos, containing far fewer galaxies than expected for an area of its size. To put this into perspective, if the universe were evenly distributed, we would expect thousands of galaxies to occupy this space. Yet within the Boötes void, only a handful of galaxies have been identified. The sheer scale of this emptiness challenges our current models of how galaxies form and cluster under the influence of gravity. Standard theories suggest that matter in the universe coalesced over billions of years into a vast web-like structure, with galaxies aligning along dense filaments and clusters, while voids naturally formed in the less dense regions. However, the Boötes void is so immense and so devoid of galaxies that it defies this framework. How could such a massive region of space end up so unusually barren? Some scientists have speculated that mergers of smaller voids could have created this supervoid, but this explanation doesn't fully solve the puzzle. Another consideration is the possibility of unknown processes influencing the distribution of matter on such vast scales. The implications are profound. If regions like the Boötes void exist on this monumental scale, it forces us to rethink the uniformity of the universe and its underlying structure. Understanding the Boötes void might even offer clues to how dark energy, the mysterious force accelerating the expansion of the universe, interacts with cosmic structures. As research continues, every new discovery about this vast, empty expanse brings us closer to unraveling the mysteries of how the universe came to be as we observe it today. Next, we journey to a discovery that startled astronomers and left them speculating about the nature of interstellar visitors. The first known object from another star system, the enigmatic Oumuamua. Now turning to one of the most mind-bending concepts in our exploration, we arrive at the idea of quantum fluctuations and their potential role in the birth of the universe. At first glance, the term quantum fluctuations might sound like an abstract concept buried deep within physics textbooks, but at its core, it refers to something profoundly fascinating. In the realm of quantum mechanics, even what we perceive as an empty vacuum is far from truly empty. Instead, it is a seething field of energy where particles and antiparticles spontaneously appear and disappear in fleeting moments. These tiny fluctuations, occurring on unimaginably small scales, might hold the key to understanding the very origins of everything we see around us. Here's the idea. Some scientists propose that the entire universe could have emerged from one of these quantum fluctuations in a vacuum. Imagine a moment where there was no matter, no time, no space, only the quantum vacuum. A random fluctuation could have provided the spark, setting off the chain reaction that led to the Big Bang, the event that marked the universe's explosive beginning. This concept challenges our traditional understanding of nothingness, suggesting that even the void itself is brimming with potential, but it does not stop there. The implications are profound, touching not only on science but also on philosophy. One of the most pressing questions is how something as vast as the universe could arise from essentially nothing. Does this mean that the laws of physics, as we understand them, inherently allow for the spontaneous birth of universes? And if so, could this imply that our universe is just one of many, a small bubble in a grander cosmic multiverse? Such questions stretch the limits of human comprehension, but they also inspire deeper investigation into the nature of reality and existence. Scientists are still probing this idea from multiple angles, using powerful particle accelerators to study quantum fields and exploring the remnants of the Big Bang through cosmic microwave background radiation. Each piece of evidence brings us closer to understanding whether these fluctuations can truly account for the creation of our universe. As we continue to push the boundaries of what we know, theories like this remind us just how mysterious and astonishing our universe truly is. Next, we turn to a legendary event that sent shockwaves through the scientific community, a mysterious radio signal that lasted 72 seconds and remains unexplained to this day. As the next challenge unfolds, let's dive into an enigma that has perplexed astronomers for decades, the legendary WOW signal. Detected in the summer of 1977 by a radio telescope in Ohio, this mysterious signal lasted for 72 seconds and has never been explained or replicated since. While scanning the skies for radio signals that might hint at extraterrestrial life, astronomer Jerry Amon stumbled upon a sudden, powerful burst of energy in the data. Its intensity and clarity stood out so dramatically that he circled the signal on the printout and famously scribbled the word "wow" next to it, giving the signal its name. What made it so astonishing was its unique combination of characteristics. It was incredibly strong, seemingly coming from deep space in the direction of the constellation Sagittarius, and unlike any natural radio signal ever observed. For decades, scientists have scoured the skies in hopes of finding another signal like it, but the WOW signal remains a singular event. Was it a message from an intelligent extraterrestrial civilization, a one-off cosmic anomaly, or perhaps even an unknown human-made interference? Despite numerous theories, including the possibility of a comet passing by at just the right time, none have definitively explained it. The WOW signal holds immense significance in the search for intelligent life beyond Earth because it suggests that something truly extraordinary might be out there, waiting to be discovered. Yet, its fleeting nature has left us with more questions than answers, spurring decades of research and debate. As we continue to scan the cosmos using ever more advanced technology, the legacy of the WOW signal fuels the hope that one day we might finally understand its origin or receive a new signal that might change everything we know about our place in the universe. Now, let's journey into the mysterious realm of rogue planets, wandering alone in the vast darkness of space. Now turning to the fascinating case of rogue planets, let us explore these solitary wanderers of the cosmos. Unlike the planets in our solar system, which obediently orbit around the Sun, rogue planets are untethered, drifting freely through the galaxy without a star to call home. These nomadic worlds challenge everything we thought we understood about planetary formation. Conventional theories suggest that planets form within the swirling disks of gas and dust around young stars, eventually settling into stable orbits. But rogue planets appear to have broken those rules, either forming independently in the vast emptiness of space or being violently ejected from their original star systems. What makes these planets even more intriguing is the possibility that, despite their isolation, they could harbor life. With no sunlight to provide energy, one might assume they would be cold, barren, and inhospitable. However, scientists speculate that some rogue planets might generate heat through internal processes like radioactive decay or gravitational interactions. If such a planet has a thick atmosphere or a subsurface ocean insulated by ice, it could potentially create conditions suitable for microbial life. Imagine a world shrouded in perpetual darkness, illuminated only by faint starlight from distant stars or the eerie glow of its own geothermal activity. These planets remain elusive as their faint presence is incredibly difficult to detect without the light of a nearby star to reveal them. Astronomers typically rely on techniques like gravitational microlensing, where the gravity of a rogue planet bends and magnifies the light of a background star, creating a brief, detectable signal. Each discovery of a rogue planet opens up new questions about the diversity and resilience of planetary systems and the possibilities for life in unimaginable environments. As we continue to refine our technology and expand our search, the mysteries of these wandering worlds remind us just how much of the universe remains unexplored. Coming up next, let us delve into the mystifying phenomenon of fast radio bursts, sudden and powerful signals from distant galaxies that have yet to reveal their true origins. Moving forward, we arrive at the puzzling case of fast radio bursts, a phenomenon that has left astronomers scratching their heads for over a decade. Fast radio bursts are sudden, incredibly powerful bursts of radio waves originating from galaxies millions to billions of light-years away. Lasting only milliseconds, these enigmatic signals pack more energy in an instant than our Sun produces in an entire day. What makes them even more intriguing is their behavior. Some fast radio bursts occur only once, like brief cosmic whispers, while others repeat irregularly, as though they are echoing messages from a distant corner of the universe. The potential explanations are as fascinating as the phenomenon itself. One theory suggests that fast radio bursts could be the result of catastrophic cosmic events, such as the collision of neutron stars or the collapse of a massive star into a black hole. These dramatic scenarios account for the burst's immense energy and the fact that many are one-time events. However, the repeating bursts are more mysterious, leading scientists to explore alternative possibilities. Some suggest they might be caused by highly magnetized neutron stars called Magnetars, which periodically release powerful flares of energy. But then, there is the more provocative idea. Could fast radio bursts be signals from advanced extraterrestrial civilizations? While there is no direct evidence to support this, the possibility keeps imaginations alive and motivates researchers to keep looking. Detecting these bursts is no easy task. They are so brief and random that capturing one requires specialized radio telescopes scanning vast areas of the sky. Once detected, astronomers analyze their unique properties, such as their dispersion, which provides clues about their origin and the space they traveled through. Interestingly, the study of fast radio bursts is not only about solving a mystery, but also about using them as tools to explore the universe. Their signals pass through intergalactic gas and plasma, allowing scientists to map otherwise invisible matter between galaxies. As technology advances and observations grow more refined, we edge closer to understanding what or who might be behind these cosmic signals. Could they hold answers to questions we have yet to ask, Or are they simply another reminder of how vast and unpredictable the universe truly is? Coming up, we will explore the perplexing mystery of why our universe seems to favor matter over antimatter, a fundamental imbalance that defies the very laws of physics themselves. Now turning to the enigma of the missing antimatter, we delve into one of the most profound puzzles in modern cosmology. According to the Big Bang theory, the universe should have been born with equal amounts of matter and antimatter. For every particle of matter, there should have been a corresponding antiparticle with the same mass but opposite electric charge. When matter and antimatter meet, they annihilate each other, releasing pure energy. This symmetry suggests that the universe should have essentially been wiped out in a flash of light shortly after its creation, leaving nothing behind, not stars, not planets, not even us. Yet here we are, living in a universe overwhelmingly dominated by matter. So, where did all the antimatter go? Scientists have been grappling with this question for decades, as it challenges the very foundation of our understanding of the cosmos. One prevailing theory is that a tiny imbalance existed between matter and antimatter during the earliest moments after the Big Bang. For every billion particles of antimatter, there may have been one extra particle of matter. When the mutual annihilation occurred, this minute surplus of matter was left behind, forming the universe as we know it. But what caused this imbalance? To explore this, physicists have conducted numerous experiments at particle accelerators, recreating the high-energy conditions of the early universe. These experiments have revealed subtle differences in how matter and antimatter behave, a phenomenon known as charge parity violation. While intriguing, the observed differences so far are not nearly enough to explain the vast dominance of matter in the universe. Another avenue of investigation is the search for primordial antimatter. If large amounts of antimatter somehow survived, they might reside in distant regions of the universe, forming antimatter galaxies or stars. However, no definitive evidence of such structures has been found. This leaves open the tantalizing possibility that new physics, laws and principles that go beyond our current understanding, might hold the key to solving this riddle. Could it suggest undiscovered particles, forces, or interactions that tip the scales in favor of matter? Or does the mystery hint at something even more profound about the nature of our universe? As researchers continue to push the boundaries of knowledge, the missing antimatter mystery serves as a reminder of how much we still have to learn about the cosmos. Up next, we will dive into yet another cosmic anomaly, the cold spot, a chilling feature in the fabric of the universe that defies explanation and raises questions about the very nature of reality. As the next phase of the journey unfolds, we find ourselves gazing into the depths of the universe at a peculiar anomaly known as the cold spot. Discovered in the cosmic microwave background, the faint leftover radiation from the Big Bang, this region appears significantly colder than the surrounding areas. The cosmic microwave background is typically uniform in temperature across the sky, so finding an area this anomalously cold is like spotting a single drop of ice in an otherwise tepid sea. Spanning a staggering 1 billion light-years, the cold spot stands out as a cosmic oddity that defies the expectation of uniformity in the universe's earliest light. What could have caused such a baffling feature? One of the leading theories suggests that the cold spot could be the result of a massive cosmic void, an enormous region of space with a much lower density of galaxies and matter than its surroundings. If such a void exists, light passing through it would lose energy due to the gravitational effects of the sparse matter within, creating the colder appearance. However, even this explanation struggles to fully account for the extent of the temperature difference observed. Another, far more speculative hypothesis ventures into the realm of multiverses. Some scientists have proposed that the cold spot could be evidence of our universe colliding with another universe in the distant past, leaving a sort of bruise on the cosmic microwave background. If true, this would represent not just a solution to the cold spot's mystery, but a groundbreaking revelation about the nature of reality itself. However, this idea lies on the fringes of theoretical physics and is far from proven. Others still suggest the anomaly could arise from unknown physical processes or phenomena that challenge our current understanding of cosmology. Whether the cold spot is a doorway to new physics, a relic of the universe's chaotic infancy, or merely a statistical fluke remains to be seen. Scientists continue to investigate this chilling enigma, using advanced telescopes and simulations to probe its origins. While the cold spot raises profound questions, it is also a powerful reminder of how much remains undiscovered about the cosmos. Moving forward, we turn our attention to another perplexing cosmic phenomenon, the Hubble tension problem, a puzzling inconsistency in measuring the universe's expansion rate that has left scientists searching for answers. With the next phase of the journey in sight, we dive into the perplexing Hubble tension problem, a cosmic quandary that has sparked intense debate among scientists. At its heart lies a fundamental question: how fast is the universe expanding? This might seem straightforward, but the answer depends on how it is measured, and that is where things get complicated. One method involves observing nearby galaxies and using a kind of celestial yardstick known as Cepheids variables. These are stars with a predictable relationship between their brightness and pulsation, allowing astronomers to calculate distances with remarkable precision. From there, they can determine how quickly these galaxies are moving away from us, leading to an estimate of the universe's expansion rate. Another approach, however, looks at the much more distant reaches of space using the cosmic microwave background, the faint echo of the Big Bang. This ancient light provides a snapshot of the universe when it was just a few 100,000 years old, and allows scientists to infer the expansion rate based on the conditions of the early cosmos. Here is the kicker: the numbers from these two methods do not match. The rate calculated using nearby galaxies is faster than the rate derived from the cosmic microwave background. This discrepancy is not just a minor rounding error. It is a significant gap that current theories of cosmology cannot easily bridge. Some scientists argue that this could be the result of unknown systematic errors in one or both measurement techniques. Others propose that it might point to entirely new physics beyond the standard model of cosmology. Could there be an undiscovered form of energy or matter influencing the universe's behavior? Or might the laws of gravity themselves need revision? The Hubble tension problem forces us to confront the possibility that our understanding of the cosmos is incomplete. As researchers refine their methods and gather more data, the hope is that these conflicting measurements can be reconciled. Whatever the outcome, solving this puzzle could unlock profound insights into the nature of the universe. But as we ponder this cosmic mystery, let us now shift our focus to another mind-bending phenomenon: the exotic and extreme climates of distant exoplanets, worlds that challenge our very ideas of what planets can be. Now turning to the extreme and uncharted realms of exoplanet climates, we encounter worlds so bizarre they seem to defy all logic. Imagine a planet where it rains molten glass sideways at speeds of thousands of miles per hour, or another where the atmosphere burns hotter than the surface of some stars. These are not figments of science fiction, but real exoplanets that exist far beyond our solar system. Take, for example, the infamous HD 190737b, a gas giant with winds so ferocious that they whip molten glass particles around the planet, creating a surreal and deadly environment. Or consider WASP 12b, a hot Jupiter so close to its parent star that its atmosphere reaches temperatures exceeding 4,000 degrees Fahrenheit, hotter than some stars, and is slowly being stripped away by the star's intense radiation. And then there is Kelt 9b, a planet where molecules cannot even stay intact due to the searing heat, making it one of the most extreme places we have ever discovered. These extraordinary conditions challenge our understanding of how atmospheres form and behave, pushing the boundaries of what we thought was possible for planetary science. How can such planets exist, and what does their bizarre nature teach us about the formation and evolution of planets across the universe? The study of these extreme exoplanets also raises tantalizing questions about the possibility of life in hostile environments, prompting scientists to rethink the criteria for habitability. If such alien worlds exist in abundance, what else might be out there waiting to surprise us? As we marvel at these distant, otherworldly climates, it becomes clear that the diversity of planets in the universe is far greater than we ever imagined. But this is only one piece of the cosmic puzzle. With these strange new worlds lingering in our thoughts, let us now delve into another mystery of the universe, the enigma of ultra-high-energy cosmic rays, particles that strike our planet with energies so intense they surpass anything we can explain. As the next challenge unfolds, we encounter the perplexing mystery of ultra-high-energy cosmic rays, particles that bombard Earth with energies so immense they defy explanation. These are not the typical cosmic rays that originate from the Sun or nearby stars. No, these are particles traveling at nearly the speed of light with energies so colossal that they outstrip anything humanity can produce, even in our most powerful particle accelerators. What makes these rays even more enigmatic is their source. Scientists have proposed various origins, ranging from the explosive remnants of supernova to the violent surroundings of black holes. Some theorize that they could be jets of particles propelled by active galactic nuclei, the intensely energetic centers of some galaxies. Others suggest that these rays might originate from events so exotic and rare that they push the boundaries of known physics. Perhaps collisions between dark matter particles or the decay of hypothetical particles left over from the Big Bang are responsible. Despite decades of study, their exact source remains one of the great unsolved mysteries in astrophysics. Even detecting these rays is a challenge, as they often collide with Earth's atmosphere, creating a cascade of secondary particles that spreads over large areas. Using advanced observatories like the Pierre Auger Observatory, researchers have tracked these secondary particle showers, but the mystery persists. What is the true nature of these ultra-high-energy cosmic rays, and what do they reveal about the most extreme processes in the universe? These questions not only challenge the limits of modern astrophysics, but also open the door to entirely new realms of scientific inquiry. As we ponder these mysterious visitors from the cosmos, we are reminded that space continues to humble us with its inexplicable phenomena. And while these particle messengers leave us with more questions than answers, they also fuel our curiosity to explore further. Now, with our attention fixed on the farthest reaches of space, let us turn to yet another compelling cosmic puzzle, the horizon problem, a conundrum that challenges our very understanding of the universe's uniformity. Now turning to the horizon problem, we find ourselves grappling with one of the most perplexing questions in cosmology. Why is the universe so strikingly uniform in temperature? When we look at the cosmic microwave background, the faint afterglow of the Big Bang that permeates the universe, its temperature is nearly the same no matter which direction we measure. This might seem unremarkable at first. After all, why wouldn't the universe be consistent? But here's the catch. The universe is so vast that regions of space on opposite sides of the sky have never been in contact with each other. In other words, they are so far apart that light, the fastest thing in the universe, could not possibly have traveled between them since the beginning of time. According to the laws of physics, these regions should not have been able to exchange energy or information, and yet they display an almost identical temperature. This defies the expectation that the universe should be patchy or uneven, given its isolated pockets. So how do we explain this bewildering level of uniformity? Enter the theory of cosmic inflation. This groundbreaking idea suggests that in the first tiny fraction of a second after the Big Bang, the universe underwent an unimaginably rapid expansion, growing exponentially in size. During this brief yet extraordinary period, regions that were once close enough to exchange information were stretched far apart. inflation essentially smoothed out the wrinkles in the fabric of space-time, creating the uniform cosmos we observe today. While cosmic inflation elegantly resolves the horizon problem, it raises new questions of its own. What exactly triggered this period of inflation? What kind of energy powered it, and why did it eventually stop? These mysteries remain unsolved, keeping the horizon problem at the forefront of cosmological research. As we marvel at the way inflation reshaped our understanding of the early universe, we are reminded that each answer in science often leads to a cascade of new questions. And with that, let us journey further and uncover another enigma of the cosmos, the strange and captivating hexagonal storm at the North Pole of Saturn. Now turning to the enigma of Saturn's hexagon, we encounter one of the most visually stunning and scientifically baffling mysteries in our solar system. At the North Pole of Saturn lies a massive, six-sided jet stream, an enormous geometric feature stretching nearly 20,000 miles across. First discovered by the Voyager spacecraft in the early 1980s, this peculiar hexagon has continued to captivate researchers, especially since its intricate details were revealed by the Cassini mission decades later. Unlike anything seen on other planets, this persistent pattern defies conventional atmospheric theories. After all, how could nature, driven by chaotic and fluid dynamics, produce something so precise and stable over such a long time? Scientists have speculated that the hexagon is the result of a complex interplay between Saturn's fast-moving winds and its internal rotation. Laboratory experiments simulating fluid behavior on a rotating sphere have demonstrated that under certain conditions, polygonal shapes can emerge. This might explain how the hexagon forms and remains stable, but it does not fully unravel the mystery. Questions abound. Why is it a hexagon and not some other shape? What determines its edges and corners so perfectly? And perhaps most curiously, why don't similar features appear on other gas giants like Jupiter? Adding to the intrigue, the center of Saturn's hexagon contains a strange and enormous stationary hurricane, with a calm eye surrounded by violent storms whipping at over 300 miles per hour. Despite decades of study, the true cause of this hexagonal phenomenon remains unknown, challenging our understanding of planetary atmospheres. Much like Saturn itself, with its dazzling rings and swirling storms, the hexagon stands as a reminder that even within the familiar confines of our solar system, space continues to defy explanation. And speaking of mysteries that stir the imagination, let us now dive into the incredible tale of Eta Carinae, a star system that defied death with an eruption so powerful it reshaped our understanding of stellar evolution. Moving forward, we arrive at the awe-inspiring and perplexing tale of Eta Carinae, a star system that, in the mid-1800s, made its mark on the night sky with an outburst so intense it was visible from Earth with the naked eye. This event, known as the Great Eruption, was so powerful that for a brief period, Eta Carinae became the second brightest star in the sky, outshone only by Sirius. But here's where things take an astonishing turn. This wasn't a supernova. Despite expelling an immense amount of material, forming the beautiful yet mysterious homunculus nebula, the star survived the eruption. Such behavior is virtually unheard of in stellar physics. Stars of Eta Carinae size, often referred to as hypergiants, typically end their lives in catastrophic supernova explosions, collapsing into either neutron stars or black holes. Yet somehow, Eta Carinae defied the script. It released as much energy as some full-blown supernova, rivaling the power of millions of suns, and still managed to remain intact. This confounding survival has left scientists grappling with questions. Was the Great Eruption the result of a rare internal instability? Could it have been triggered by interactions with a massive companion star within this binary system, causing gravitational mayhem? Or does this event hint at an entirely new class of stellar phenomena? Adding to the enigma, Eta Carinae continues to be unstable to this day. Its luminosity fluctuates unpredictably, and it emits intense stellar winds that blast material into space at millions of miles per hour. Observations suggest that its fate might still lead to a supernova or perhaps something even stranger. The Great Eruption of Eta Carinae remains a puzzle that challenges our understanding of how massive stars live and die, proving once again that the cosmos often writes its own rules. As we move from explosions that defy expectations to paradoxes that threaten the foundations of physics itself, let us now explore the mind-bending mystery of black hole information and the profound questions it raises about the universe. Now turning to the next cosmic enigma, let us unravel the perplexing mystery of the black hole information paradox, a puzzle that has baffled physicists for decades. At its core, this paradox challenges one of the most fundamental principles of physics, the conservation of information. In essence, the laws of quantum mechanics dictate that information, the essential blueprint of particles and their states, cannot simply vanish from the universe. But black holes, those mysterious cosmic sinkholes with gravity so intense that nothing, not even light, can escape, seem to break this rule. When matter or energy falls into a black hole, it carries with it specific information about its properties. Yet, as the black hole emits what is known as Hawking radiation, a process predicted by renowned physicist Stephen Hawking, it gradually loses mass and energy over time. Eventually, the black hole may evaporate entirely, leaving behind no trace of the original information. This apparent erasure of data stands in direct contradiction to quantum mechanics and has set the stage for one of the most profound debates in modern physics. Could it mean that information truly ceases to exist, defying everything we know about the universe? Or are we simply missing a deeper understanding of how black holes function? Some theories suggest that information might not be lost but rather encoded in the Hawking radiation itself, though this has yet to be proven. Others propose that the information could be stored on the black hole's event horizon, a concept aligned with the idea that the universe could operate like a vast hologram. Even more speculative ideas hint that black holes might serve as gateways to parallel universes, where the information escapes to an entirely different reality. Resolving the black hole information paradox is not just a matter of understanding these enigmatic objects. It could unlock groundbreaking insights into the very fabric of reality, potentially bridging the gap between quantum mechanics and Einstein's general theory of relativity. As researchers continue their quest to solve this cosmic riddle, they stand on the brink of discoveries that could fundamentally redefine our understanding of space, time, and the laws governing the universe. With the paradox of black holes fresh in our minds, let us now turn our attention to another cosmic conundrum that blurs the boundaries of physics and perception, the double-slit experiment. As the next challenge unfolds, we delve into an experiment that defies logic and stretches the very fabric of our understanding of the universe, the double-slit experiment. This groundbreaking test, first performed by Thomas Young in the early 1800s and later extended into the realm of quantum mechanics, reveals behavior so bizarre it has perplexed physicists for centuries. The setup is deceptively simple. Particles such as electrons or photons are directed at a barrier with two parallel slits, and a screen is placed behind to capture where they land. If one slit is open, the particles form a pattern directly behind it, as expected. But when both slits are open, something extraordinary happens. A wave-like interference pattern appears on the screen, as though the particles had traveled through both slits simultaneously, interacting with themselves like ripples in a pond. This startling result demonstrates that particles can behave as waves, a notion that challenges our classical understanding of matter. But the mystery deepens when the experiment is altered to observe which slit the particle travels through. When measurement devices are added to track the particles, the interference pattern disappears, and the particles behave like tiny solid objects passing through one slit or the other, as if they knew they were being watched and changed their behavior in response. This astonishing phenomenon, known as wave-particle duality, suggests that the act of observation itself influences reality, collapsing the probabilistic wave-like behavior into a definitive particle state. Such implications go far beyond the laboratory, raising profound questions about the interplay between consciousness and the physical universe. Could it mean that reality at its most fundamental level is shaped by observation? Or is our understanding of quantum mechanics merely scratching the surface of truths far stranger than we can imagine? The double-slit experiment doesn't just challenge long-held assumptions about particles and waves. It invites us to reconsider the nature of existence itself. Some even speculate that it hints at the role of observers in shaping the cosmos, a concept that ties into the deeper questions of whether the universe is deterministic or probabilistic in its design. While no consensus has been reached, this iconic experiment remains a cornerstone of quantum theory and a gateway to exploring the fascinating intersection of physics, philosophy, and the unknown. Moving forward, we now shift our gaze to the Planck scale, a domain where the rules of space and time dissolve into quantum chaos, and the boundaries of our scientific understanding are pushed to their limits. Now turning to the Planck scale, we enter a realm so minuscule and extreme that it defies all conventional frameworks of physics, a domain where the known laws of the universe are no longer reliable. The Planck scale refers to incredibly tiny measurements of length, time, and energy, where quantum effects of gravity become significant. To put it into perspective, the Planck length is roughly 20 quintillion times smaller than the diameter of a proton, a concept so staggering that it almost breaches the limits of human comprehension. At this level, the very fabric of space and time appears to dissolve into what can only be described as quantum chaos. The smooth spacetime continuum predicted by Einstein's theory of relativity is replaced by a seething, frothy landscape of quantum fluctuations. Here, particles pop in and out of existence, and the traditional notion of cause and effect begins to unravel. This chaotic microcosm isn't just a theoretical curiosity, it represents the frontier of modern physics. It's the scale at which gravity must be reconciled with quantum mechanics, a long-standing challenge that has eluded scientists for decades. The Planck scale is also where hypotheses like string theory and quantum loop gravity attempt to unify our understanding of all fundamental forces into a single, cohesive framework. But despite years of research, we have yet to develop tools or experiments capable of probing this enigmatic scale directly, leaving it shrouded in mystery. What's perhaps most fascinating is the implication that the Planck scale may hold the key to explaining the birth of our universe. Some theorists suggest that the Big Bang itself emerged from quantum phenomena at this level, meaning that understanding the Planck scale could unlock answers to the ultimate questions of existence. As we stand on the edge of this great unknown, one thing is clear. The Planck scale is not just a puzzle for physicists, but a profound reminder of how much we have yet to uncover about the fabric of our reality. And with this exploration, we bring our journey to a close, having delved into 25 awe-inspiring ways space defies scientific laws. But one question lingers: what mysteries could yet await us, hidden beyond the limits of human perception? Now turning to further explorations of dark energy, we revisit one of the most perplexing mysteries in cosmology. Dark energy, the force driving the accelerating expansion of the universe, continues to defy all expectations, leaving scientists grappling with its true nature. Could this mysterious phenomenon be linked to the strange and counterintuitive principles of quantum physics? Some theories suggest that dark energy may arise from quantum fluctuations in the vacuum of space, an idea that hints at a deep connection between the quantum world and the large-scale structure of the universe. Imagine if the energy of empty space, which is far from truly empty, could hold the answers to why the universe expands faster over time. Even more astonishing is the possibility that dark energy might point to the existence of other universes. Theoretical models propose that our universe could be just one of many within a vast multiverse, with each universe governed by different physical laws and values of dark energy. If true, this would radically transform our understanding of reality, suggesting that the cosmos we know is just a small part of something unimaginably larger. Looking ahead, the future of dark energy research holds both promise and challenge. Upcoming space missions and observatories like advanced telescope arrays aim to uncover more clues about dark energy's role in shaping the cosmos. These efforts may allow us to map the expansion of the universe with even greater precision, potentially revealing hidden patterns that could lead to groundbreaking discoveries. There's also growing interest in how dark energy might intersect with emerging theories in quantum mechanics, perhaps offering a unified explanation that ties together the forces of nature. As we continue to probe this enigma, one thing is certain: dark energy not only challenges the boundaries of science but also inspires us to rethink our place in the universe. Could solving this puzzle unlock secrets that transform our understanding of existence itself? While answers remain elusive, the pursuit of dark energy's mysteries promises to be one of the most exhilarating frontiers of discovery in the years to come. With the next phase of the journey in sight, we delve into the curious anomaly known as the cold spot. This vast, frigid region in the cosmic microwave background has perplexed scientists since its discovery, standing out as colder than the surrounding space and defying the expected uniformity of the early universe's remnants. But what could account for this chilling irregularity? One of the most tantalizing theories suggests that the cold spot could be evidence of a parallel universe brushing against our own. Imagine for a moment that our universe is just one of countless others floating within a larger multiverse, and the cold spot represents a cosmic scar from where two universes might have collided or interacted. Such a possibility, while speculative, would drastically expand our understanding of existence, offering a glimpse into a realm far beyond our current scientific grasp. Alternatively, another leading explanation is that the cold spot could be the result of a massive cosmic void, an immense region nearly devoid of galaxies and matter. This would cause light traveling through the area to lose some of its energy, creating the cooler appearance we observe. Known as the Sachs-Wolf effect, this phenomenon aligns with our understanding of how light interacts with the fabric of space, though it still leaves many unanswered questions about the formation of such an immense void in the first place. The debate surrounding the cold spot continues to fuel investigations into the very nature of space itself. Could it hold clues to the fundamental structure of the universe or even hint at unseen forces at play? As researchers develop more precise tools and models, the hope is that we may one day unravel the truth behind this enigmatic feature. Whether it points to an extraordinary interaction between universes or a natural quirk of cosmic formation, the cold spot serves as a reminder of how much we still have to learn about the cosmos. Moving forward, the exploration of this anomaly pushes the boundaries of our imagination while challenging the limits of our scientific knowledge. Moving forward, we return to the Great Attractor, an enigmatic region in the cosmos whose gravitational pull has puzzled scientists for decades. Imagine an invisible force so immense that it draws entire galaxies, including our own Milky Way, toward it at astonishing speeds. Hidden behind a dense area of cosmic dust and gas known as the zone of avoidance, the Great Attractor's true nature remains shrouded in mystery. Could this gravitational anomaly be pointing us toward a groundbreaking discovery in physics? Some researchers suggest that the Great Attractor might be composed of matter we have yet to identify, potentially belonging to a new class of substances that do not interact with light in ways we can currently detect. This raises the tantalizing possibility that it could be a massive concentration of dark matter, a substance scientists believe makes up a significant portion of the universe's mass yet remains invisible to our instruments. Alternatively, others propose that its pull may be a symptom of previously unknown physical forces or principles, fundamentally challenging our understanding of gravity and how it operates on the largest scales. Theories even speculate that the Great Attractor could be part of an even larger structure, known as the Laniakea supercluster, a colossal system of galaxies interconnected by their movements through space. If true, this would point to a cosmic web of matter so vast and interconnected that it redefines our place within the universe. And yet, for all these theories, the Great Attractor still refuses to reveal its secrets fully. As scientists continue to refine their observations with advanced telescopes and simulations, they hope to shed light on this elusive phenomenon. Could the answer to this puzzle reshape our understanding of the universe's structure, or will it unveil entirely new physics that we cannot yet fathom? While the Great Attractor's mystery persists, it serves as a fascinating testament to the universe's ability to both inspire and confound us in equal measure. As we ponder this cosmic enigma, our journey takes us to another baffling signal from space, the strange bursts of energy known as fast radio bursts. Now turning to the enigmatic phenomenon of fast radio bursts, these sudden, intense flashes of radio waves from distant galaxies have left scientists both amazed and perplexed. Lasting only milliseconds, these bursts pack more energy than the sun emits in an entire day. First discovered in 2007, fast radio bursts were initially thought to be one-off events, but recent observations have revealed some that repeat in mysterious patterns, igniting debates about their origins. Could these bursts be natural astrophysical phenomena, or do they hold the tantalizing possibility of being signals from advanced extraterrestrial civilizations? Some researchers suggest that fast radio bursts may be the result of cataclysmic events, such as the collision of neutron stars or the collapse of massive stars into black holes. Others have proposed they could originate from magnetars, neutron stars with incredibly powerful magnetic fields that occasionally unleash enormous amounts of energy. But the repeating bursts complicate these theories, as they suggest a more stable, ongoing process rather than one-time cosmic events. This has led some to speculate on more exotic explanations, including the possibility that these signals could be produced intentionally by intelligent life. Some scientists hypothesize that fast radio bursts could be the byproduct of advanced alien technology, perhaps powerful energy beams used to propel spacecraft across interstellar distances. If true, this would represent humanity's first glimpse into the activities of a civilization far more advanced than our own. While these theories are still speculative, the search for answers has already led to groundbreaking advancements in radio astronomy. With the deployment of new, highly sensitive telescopes capable of detecting and pinpointing the origin of these bursts, researchers are now closer than ever to unraveling their mysteries. Whether they prove to be natural or artificial in origin, fast radio bursts serve as a reminder of how much we have yet to understand about the universe. As we explore these celestial signals, they push us to ask deeper questions. Are we truly alone, or are these bursts the distant echoes of another intelligent species reaching out across the cosmos? With the hunt for answers fueling both scientific innovation and philosophical wonder, the mystery of fast radio bursts keeps humanity firmly focused on the skies. And as these captivating signals beckon us to search for life beyond Earth, another enigma awaits, one hidden deep in the fabric of the universe itself. The perplexing phenomenon of quantum fluctuations and their link to the universe's very origin. Now turning to the quantum fluctuations debate, we delve into one of the most fascinating and mind-bending ideas in modern physics. Quantum fluctuations refer to the tiny, spontaneous changes in energy that occur even in the emptiest regions of space, and they are believed to have played a fundamental role in the birth of the universe. Imagine this: what we perceive as nothingness is not truly empty. Instead, it is an active, seething field of energy where particles and antiparticles momentarily appear and disappear, governed by the strange rules of quantum mechanics. According to one leading theory, these fluctuations in the quantum vacuum could have triggered the massive expansion of space known as cosmic inflation, which set the stage for the development of galaxies, stars, and everything else in existence. But how can these microscopic, fleeting changes in energy lead to something as enormous as the universe itself? Scientists propose that during the early universe, these fluctuations were stretched to cosmic scales by the rapid inflationary expansion, imprinting the seeds of structure that would later grow into the galaxies we observe today. However, not all physicists agree on the details, and competing theories have emerged to challenge this explanation. Some researchers argue that quantum fluctuations alone cannot account for the uniformity and large-scale structure of the universe. They suggest additional mechanisms, such as variations in the physics of different regions of space or even influences from beyond our observable universe. Others take an even more radical approach, proposing that quantum fluctuations might point to the existence of a multiverse, a collection of parallel universes, each governed by slightly different laws of physics. This raises profound questions. If quantum fluctuations gave rise to our universe, could they also be responsible for countless other universes, each with its own unique reality? The scientific community is actively testing these theories through advanced experiments and observations. For instance, researchers analyze the cosmic microwave background, the faint afterglow of the Big Bang, for tiny patterns and irregularities that could reveal the fingerprints of quantum fluctuations stretched during inflation. Meanwhile, particle physicists are pushing the boundaries of what we know about quantum fields by conducting experiments using powerful particle accelerators, attempting to replicate the extreme conditions of the early universe. These efforts are helping to sharpen our understanding of quantum mechanics, cosmology, and the fundamental nature of reality itself. As we unravel the mysteries of quantum fluctuations, we are forced to confront a deeper philosophical question. Can we ever truly understand the origin of the universe, or are there limits to human knowledge? These unanswered questions fuel the relentless quest for discovery, reminding us that even the smallest, most fleeting phenomena can hold the key to the largest mysteries of existence. And while the debate over quantum fluctuations rages on, another cosmic puzzle beckons us, one that challenges our understanding of balance in the universe. Moving forward, we tackle the missing antimatter mystery, a conundrum that has perplexed scientists for decades. As we reflect on these 25 astonishing cases where space has defied the very laws of science, it's clear that our universe is far more mysterious and complex than we could ever have imagined. From the unexplained forces affecting spacecraft trajectories to the mind-boggling implications of quantum fluctuations, each mystery pushes us to rethink the fundamental principles we once took for granted. These phenomena remind us that in the vast expanse of the cosmos, our understanding is only beginning to scratch the surface. They challenge not just what we know, but how we know it, opening the door to questions that extend beyond science into the very essence of existence. So, what will the universe surprise us with next? Perhaps new discoveries await just beyond the horizon, ready to shatter old paradigms and introduce new ones. If these mysteries have sparked your curiosity, we want to hear from you. Which of these cosmic puzzles fascinated you the most, or do you have your own favorite space mystery that we didn't mention? Share your thoughts in the comments below and join the conversation. And don't forget to subscribe to our channel for more explorations into the wonders and enigmas of the universe. Hit that notification bell so you never miss out on our journey through the cosmos. Until next time, keep looking up and wondering, because out there, the answers are limitless.